Greetings. My name is Maria Rivera. I'm an artist living and working in southwestern Connecticut. I focus most of my art making on oil painting, and I would like to present a brief introduction to the chemistry that makes painting possible, specifically pigments, such as these, and why it's important for an artist to know the differences and limitations of these pigments. First, the oldest known and most basic pigments date back at least 30,000 years, exemplified by the Paleolithic cave paintings in Lascaux Cave, France, and Altamira Cave in Cantabria, Spain. These are referred to as earth pigments, which are basically charcoal with added variations of iron oxide. White pigment was achieved by oxidizing lead. They are light-fast, meaning they won't fade from exposure to ultraviolet or daylight, and are relatively inexpensive to produce. Added to various binders such as linseed oil, egg tempera, and gum arabic, they have been used all this while. Because earth pigments tend to absorb oil, however, contemporary oil painters use them mostly as underpainting, which is the base layer of an image, or for what is considered traditional painting, in which the artist uses these pigments for all layers of the image. Any of Da Vinci's, Rembrandt's, or Bruegel's, such as this scene, known as Census at Bethlehem, illustrate this property. They are primarily brown, with sparing use of brighter color. Until the late 19th and early 20th centuries, bright colors were obtained either by grinding semi-precious minerals down to powder or by rendering specific insects, mollusk shells, or animal urine. This is lapis lazuli. It exemplifies one of the semi-precious minerals that was used for pigment. It was the costliest mineral after gold, because its primary source was and remains Afghanistan. It was and can still be used for a violet blue known as ultramarine blue, literally the blue from beyond the sea. Though some of these methods produced excellent colors, this was a trial and error process, and some minerals, such as copper-based greens, tended to fade over a short span of time upon exposure to daylight or acidic atmosphere. With the development of modern chemistry in the 1800s, however, less expensive means of producing reliable substitute pigments were discovered, and artists could purchase these in tubes instead of having to grind the pigments themselves. Tube paints allowed artists to paint outdoors with relatively little mess, facilitating the plein air and impressionist methods. Fast forward to the dawning 21st century, when I decided to seriously pursue my painting opportunities. Although I had been puttering and generally experimenting since the 1970s, I lacked the solid working knowledge of the properties of the paints I used. I took notes specific to each painting on which I was working, but hadn't given much thought as to why one blue made brighter greens than another, until that is, chance discussion with an older, veteran colleague who headed a local artists association and was renting a studio space 2 floors below mine. I remember him saying, "You need to find a copy of this book," as he handed me Michael Wilcox's Blue and Yellow Don't Make Green. As I paged through it, my colleague explained that the pigments employed for the primary hues of blue, yellow, and red have a main component that's reflected back to us, as well as a secondary hue that's more subtle, and often even a third component that we don't notice until the pigment behaves differently than anticipated. Blues, for example, have either a greenish or a purplish secondary hue. So as you might see, I've labeled this is cobalt blue, that has a greenish tint, and ultramarine blue is the violet blue that has more of a purplish tint. Yellows have either a greenish or orangey secondary hue. To mix a bright green, one would use a greenish blue, such as cobalt, and a greenish yellow, such as Hansa or cadmium lemon, depending on the manufacturer. as you might be able to see there. It's a fairly bright green. Otherwise, to use a violet blue or an orangey yellow would create a duller green than that. So here are some basic charts I've prepared to illustrate this principle. So this chart on the left shows mixes of ultramarine blue with each of those main colors and the differences between the permanent rose, which is the violet red, and the cadmium red, which is the orangey red. As you might be able to see, that's the purple that the cadmium makes with the ultramarine. You can see it's much more purple looking with the permanent rose. And I added white to make it more obvious because the purple is still a dark kind of a purple. So that makes a better purple. When we come to the greens, if we compare the green that the cadmium yellow makes with the ultramarine, and I believe this is gamboge, the gamboge makes with the ultramarine, and compare that to the green of both those yellows with the cobalt blue, I think you can see that the green that they make is a brighter sort of a green. And granted, the gray backgrounds are a little different on both those charts. And these aren't the most ideal examples of it, but there is definitely a difference in these two blues. As you can see there, mixing the cobalt with one of the whites, you can see it's more of a sky blue. And with the ultramarine, it's more of a deeper sky blue, but it's got more of a purpley tone to it. Now, why is this important? For an artist, knowing these basic principles saves time and material, perhaps even expensive material. Although most paint manufacturers offer ranges of over 100 premixed tube colors, it tends to be less costly, as well as space-saving, for an artist to limit their working palette to fewer than 20 go-to colors. Lately I've been using only 8, plus 3 different whites for specific applications. Out of these, artists can mix myriad hues, tints, and shades, ensuring greater consistency in their work from image to image. Also, paint manufacturers change formulations every so often, either to produce less expensive versions of a particular color when the pigment becomes cost prohibitive, to replace a pigment thought to be light fast but that has proven otherwise, or because the pigment they've been using is no longer available. Then, it's important for an artist to know the standard chemical number, because changes in formulae can also coincide with changes in name. Paint names are not standardized, so a Hansa Yellow for one manufacturer may be a Winsor Lemon for another, which can become pretty confusing. The other main pigment consideration in mixing paints involves the relative transparency or opacity of a given pigment and how it is to be used. For example, one means of producing visual depth or evening out a tone while maintaining established depth is to apply at least one layer of glazing. Glazes are typically mixed using a medium of damar resin and a solvent, often turpentine, but this archival one I use contains lavender spike oil instead, plus a small amount of the desired color. This creates a flowing liquid suspension as opposed to a paste, which then acts like a thin layer of tinted glass, hence the term glazing. Obviously, for such a mixture, a transparent or semi-transparent pigment would work best. It's also prudent to pay attention to the light fastness of a given pigment to ensure that one's work will last at least a lifetime. So, knowing these characteristics, how does an artist know how a color they haven't used before will behave? Or how to identify the characteristics they're looking for with a different manufacturer's product line? Happily, most manufacturers label their tube paints with certain information. The standardized pigment number, also known as a color index number. This is PR 108. The light fastness rating, light fastness 1. The location of the pigment in the range from transparency to opacity, which is what this black square is, and that shows that this is an opaque pigment. The binder used, which is a linseed and safflower oils, and the chemical name of the pigment, and this one is cadmium sulfoselenide. If the label doesn't include these, there is now usually a color chart available on the manufacturer's website, as well as where the paints are sold and displayed in art supply stores. I hope I've challenged you to look more closely at your favorite paintings, to understand them at a different level. If you would like to read more about pigments, their chemistry, and their history, there are 5 books I think you may find useful. Color, A Natural History of the Palette by Victoria Finlay. The Artist's Handbook of Materials and Techniques. This is the 5th edition. There might be another one since I purchased this. This is by Ralph Meyer. The Secret Lives of Color by Cassia St. Clair. Blue and Yellow Don't Make Green and Mixing Greens by Michael Wilcox. May you see color with newfound appreciation. Thank you.